I think is, I don't know, maybe the easier one. I'll let you guys be the judge of that, but I think it's the easier one. But we'll go over it. 4B is a lot of just kind of the algebra of things. So we've defined conditional probability. It's the same exact definition. The probability of event E, given that event F occurred, is now the probability of E given F over the probability of F. That is slightly different than what we had before. What we had before was the number of E and F over the number of F. Now I'm saying that that's the same thing as the probability. And how could that be? Because by probability, I'll prove this once and then we'll never look at it again, but the probability of E and F over probability of F would technically be the probability of number would be the number of E and F over the number in the sample space over the number in F over the number in the sample space, and it cancels. And you can see that both definitions are exactly the same. And we do not need to prove that. We can consider that to be our proof. So there it is. But we can use either definition. The number of in the number of occurrence, the cardinality or probability. We can use either. So we can use this as a jumping off place. It's really that easy. So let's look at an example. Let's say the probability of event A occurring is 40%. The probability of event B is 30%. And the probability of E and B occurring is 10%. Then what must be the probability of A given that B occurred? How can we do this? Well, we can use our definition. Probability of A and B over the probability of just B. So the probability of A and B was given in the problem. It's 10%. And the probability of just B is 30%. And so that would be 1/3. That would just be 1/3. But let's look at the probability of B given that A occurred. That's going to be the probability of B and A, probability of A, and this is the exact same. So there's no, it doesn't matter the order of that. So B and A is the same thing as A and B. We don't care the order. So the numerator is the same. And the probability of A in this problem is 0.4. So that would be 1/4 or 0.25. That's another way to write it. Okay. So hopefully that makes sense. Hopefully it, hopefully it feels easy. It is easy. There's nothing too difficult about that. Let's look at another example. Let's say that the event E and F are disjoint. Okay, and we know what that means. So let's find the I need to define a few more things. No, I don't. Let's find the probability of E given F and the probability of F given E. So the only thing I know is that E and F are disjoint. If E and F are disjoint, then we know their intersection must be the empty set. Okay, so that implies that the probability of E and F must be 0. And the only other way I can think to write that is that the number in E and F is 0. Okay, so I don't even know what the probability of E and F are, but if they're disjoint, then I can certainly say the probability of E and F is 0, even though it's divided by probability of F. So this is 0 over the probability of F. So if they're disjoint, conditional probability is always going to equal 0. Probability of E, probability of E and F, probability of E, and we know that this is 0. So that must also be 0. So if they're disjoint, they're going to be 0. Okay, because there's no intersection.
Is that a hard, fast rule, or is there an exception to the rule?
No, that is it. The only exception I could possibly think, and this is a deep cut, but the only exception I could think of is we are assuming that the probability of F does not equal 0. Okay, because I'm dividing by 0. So that's the only rule that couldn't happen, or the probability of E cannot equal 0. That would be the only thing in the theory of probability. That's the only thing that couldn't happen, is I can't divide by 0. Okay.
Okay.
But other than that, we prove that if they're disjoint, then their conditional probability is 0. There's 0 chance of them happening conditionally because they have no intersection. So that's it. Okay, so hopefully that's clear. And then our friends in Venn diagram world still exist. So let's look at them. Okay. And let's call this J. And let's call this K. And let's say that this is 10%, 20%, and 30%, and 40%. Okay. Let's find the probability of K given J. That's the probability of K and J over the probability of J. If you guys, Michelle, and those watching this video have noticed yet, the second one always goes in the denominator. Okay, so hopefully that is clear by now. So the probability of K and J is the intersection. That's going to be that 20% there. And the probability of J is 10% plus 20%. So, 20% divided by 30%. Well, I could write 20 over 30, cancel the zeros, 2/3. Okay. Not too bad. Let's do a slightly harder one. The probability of K given J union K, well, that's going to be the probability of K intersect J union K over the probability of J union K. Okay. So what is the intersection of K intersect J union K? Well, J union K is anything that's in a circle. Okay. Anything that's in a circle is J union K. What does K have in common with anything that's in the circle? K. So the top part is just K. And then the probability of J union K, well, that's just anything that's in the circle. So I'm just going to rewrite this and then we'll find what the value is. So K is 20% plus 30%. And then the denominator is 10% plus 20% plus 30%. So this is 50%. 50 and 10 makes 60%. And so this would be 5/6. Okay. So hopefully that makes sense. Wish I had more room. And I wish there was a way to duplicate. In other programs, you can duplicate, like you can duplicate a slide and then you can edit it, but I don't think this one has that. Oh well. Let's do maybe not the best color. So we had J, K, 10%, 20%, 30%, 40%. Let's find the probability of J complement given K. This would be the probability of J complement intersect K, probability of K. And we remember from our discussion in set theory, J complement intersect K is just that part of K that has nothing to do with J. So the part of K that has nothing to do with J would just be 30%. And then all of K is 20% plus 30%, 30%, 50%, and that's just also going to be 3/5. I don't know why I said also. We haven't had an answer being 3/5. I don't know why I said also. But that's what I think it'd be.
Sounds good.
Okay, thank you. Next example. We don't need the Venn diagram anymore. I mean, you could, I guess you could reprove De Morgan's law through conditional probability. We don't necessarily have to, but the probability of J complement intersect K complement would be the same thing as the probability of J union K complement. So you still have De Morgan's law out there. I don't remember if it comes up in the homework, so I don't want to press it too hard, that idea, but it's still out there. It still exists. So suppose that the probability of A is equal to 50%. Probability of B is equal, probability of B given A, that's what I want to do, is 1/3. The probability of B given, what did I do? What am I doing? A, B. I think we need, let me look at my example. We have A is 1/2, B given A is 1/3. B given A find the probability of A intersect B. Okay, sorry about that. So if we're given B given A, and A, what is the probability of A and B? So the probability of B given A is defined to be the probability of A and B, or B and A, doesn't matter the order, over the probability of A. And they give me the conditional probability. They give me the denominator. So I claim I can find the numerator. So this equals 1/3 probability of A intersect B over 1/2. Okay, so we can use algebra to find this. So I will multiply both sides by 1/2 to find that. And so 1 times 1 is still 1, 2 times 3 is 6, and then these will reduce. So you will find the probability of A and B as 1/6. Not too bad. There's a lot of problems like that where you have to use algebra to solve for the missing piece. But that's pretty much it. Questions? Excuse me. Questions on that one?
Well,
There's not a ton of theory in this section. There's not many definitions that we need to go over because we've gone over so many already. We're reusing a lot of material, but there's not that much we're adding to it. We're just kind of adding conditional probability with our set theory, and we're kind of also working with a little bit of algebra with solving for particular things. So I think that's really all of the examples other than the homework that I need to show to get to the homework. So I think that would be a good place to go. And maybe we'll finish early.